interesting thing about hurricanes, though, is the damage is typically very selective. And the reason why is just like with tornadoes, if you've ever taken my Met 10 lecture class, we did exercises with this on tornadoes. But basically what happens is when you have a hurricane that's traveling and it's moving, the hurricane itself is a deep center of low pressure. And if you remember from the hand twist model, deep centers of low pressure rotate counterclockwise. Well, what this means is that the right side of the storm has winds that are actually blowing in the same direction that the storm is traveling in. So you actually get an enhancement of the wind caused by the storm's forward motion. And so over here, you would actually add the wind speeds up. So for example, let's say I have a hurricane with wind speeds of, I'll write them right here in the middle like I do with my tornadoes, 120 miles an hour. So strong Category 3 hurricane, winds of 120 miles an hour, and it's traveling north at 15 miles an hour. Over here, on the right side, where the wind is blowing in the same direction the storm is traveling in, you would have winds of 135 miles an hour. 120 plus 15 gives you 135. Meanwhile, on the other side of the hurricane, here the winds are blowing in the opposite direction that the storm is traveling in, so you actually subtract that 15. So over here you would have wind speeds of 105 miles an hour. And I'll actually show you a pretty cool example of this with Hurricane Irma in a few minutes. So the last part of Investigation 12A talks about the tracks of hurricanes. And really what they want to get here is, how do hurricanes typically, where do they form and where do they travel? And I'm going to recommend that you put your hand over the Gulf of Mexico right now and primarily just look at the storms out in the Atlantic. What typically happens out in the Atlantic is hurricanes typically form over the equatorial portion of the Atlantic Ocean, and then they begin to travel west. As they get towards the edge of the Atlantic Ocean, they begin to get tugged up to the north and eventually northeast out to sea. And this is actually a key energy distribution method. And so hurricanes actually do a lot to transfer lots of heat energy from areas near the equator up to areas near the poles. So for the next portion of this, of these two activities, this is Activity 12B, Investigation 12B, we're actually going to be looking at the evolution of a storm system. And in particular, they start by showing you Hurricane Maria. And let me tell you what you're looking at here. So what you're looking at here is what's called a time series. Down here, there are two things that are being shown: the date and then the time in UTC. If you remember, UTC is the Universal Time Coordinate. That goes all the way back to the beginning of this class when we talked about UTC. But, and then there are two things plotted on here. Plotted on this axis and in blue is the central pressure of the storm. And then plotted on this axis over here in red is the maximum sustained winds. And again, I'm not going to give too much away, but what I will tell you is if you were to connect the dots, you would see something that, again, I'm kind of doing it sloppy right now, but see, I just missed some dots right there, but you get the picture. And you can actually print this out and do it yourself as well. But here's actually what you notice. If you had to explain to somebody, like if I were to offer you $1 million to explain this to somebody, what the relationship is between minimum central pressure and maximum sustained wind speeds, you could do it by explaining how these two graphs are related to one another. And while it's not perfect, in general, there's actually a pretty good connection between Lower pressure, higher winds. This is what is called inversely proportional. When one goes up, the other goes down. And this actually makes sense due to what's called the pressure gradient force. When you have deepening pressure, that usually causes a greater difference in pressure, which then creates more wind. So you're going to do this for both Irma and Maria, but I thought I would at least show this to you to kind of give you a sense of how it works. And then the last thing I'm going to show you from this particular assignment is the actual structure of Hurricane Irma as it was getting ready to make landfall on Florida. One of the things you'll actually find as you look at the evolution of Irma's track, it actually didn't hit Miami. Instead, it actually moved over to the western coast of Florida and affected that area. But here's what you actually notice. So there's a few things here I want to point out, and then we'll be done. And the things I want to point out, first off, down here are two very important pieces of information. MSLP stands for mean sea level pressure. So this is the minimum pressure in the center of the storm. And then Vmax, this means velocity max. This is the maximum wind speed. And here it has it at 98 knots. If you wanted to convert that to miles an hour, multiply it by 1.15. Because 1 knot is 1.15 miles an hour. So, and actually the book does it for you. But one of the other things that you may notice is this storm has a pretty interesting structure to it. And one of the ways that you can identify the structure is by looking at these black lines called isotachs. These just represent lines of constant winds. There's a few interesting things you can notice. One, these don't form perfectly symmetric concentric circles around Irma. What they do, however, is, especially near the center, you see what looks like a crescent shape on the upper and right portion. This is actually the northeast portion of the eye, and this actually indicates where the strongest winds are. So the strongest winds are actually located right up here in the northeast portion of the eye. And if you actually go back to what we talked about a few moments ago, that should be expected. Right now, the storm is actually traveling towards the north, actually a little bit to the northwest, but it just so happens to be right here where the wind is blowing in the same direction that the storm is traveling in. And so right here is where the winds are the strongest. But if you actually take a look, another interesting thing is over here, so this is actually Florida itself, and if you actually notice that the winds actually decrease over land. Well, the reason why that is, and you can even see down here, the 64 knot isotach actually takes on the shape almost of the Florida coastline. Well, the reason why this happens is because of friction. So the land is much more rugged than the ocean is, and so there's much more friction. So even when you have these really intense hurricanes, as they make landfall, you begin to see a big decrease in wind speed because of friction. Another thing you'll also begin to see is hurricanes need lots of warm, moist water and warm, moist air, and when a hurricane hits land, it gets cut off from that. So what actually will eventually happen is once Irma actually hits land, it'll begin to fall apart. So that's it for this exercise. One of the things I'll warn you about is that there are some very poorly worded questions on this activity. Don't stress too much about that. I did try to throw out some hints. And if you get stuck on anything, as always, please don't hesitate to reach out to me. So that's it for this investigation, this module, and this course. So congratulations, you made it to the last activity, and you're done. So begin wrapping up, get this activity done, get the quiz done, and then you are good to go. So that's it for now. I'm Terrence Mullins. It's been a pleasure. Thank you for watching.